Start with any triangle. Now build an equilateral triangle on each side, pointing outward. Mark the center of each one and connect them. You always get a perfect equilateral triangle, every single time, no matter how weird the starting triangle is. Pause here and see if you can figure out why. Take a guess, I'll wait. This beautiful result is called Napoleon's theorem, and yes, it's actually attributed to Napoleon Bonaparte himself. Your first instinct might be to prove this with pure geometry, angle chasing, congruent triangles, the works. That would get messy fast. Instead, here's the aha moment. We'll use complex numbers. Remember the coordinate plane from algebra class? Same idea, but now every point is a complex number. The magic is that rotations become simple multiplication. Rotating a point by 60 degrees, just multiply by a complex number. That turns messy geometry into clean algebra. So the question becomes, where exactly do those equilateral triangle centers land? Let's focus on the equilateral triangle built on side AB. Remember from geometry class, the center of an equilateral triangle is just the average of its three vertices. That's the centroid, where all three medians cross. For equilateral triangles, the centroid, circumcenter, and incenter all collapse to the same point. So we need the third vertex. It sits at the midpoint of AB, pushed outward perpendicular by a factor of √3/2. And here's where complex numbers shine. Perpendicular just means multiply by I. Watch the algebra unfold on screen, and the center is simply the average of all three vertices. Now here's where the magic happens. After simplifying, watch the screen. Each center becomes a weighted combination of just two adjacent vertices. Same two weights, lambda and mu, cycling through the vertices one step at a time. See the pattern? It's perfectly cyclic. Remember arithmetic sequences from high school? Same idea of a repeating pattern, but now in the complex plane. And notice, lambda and mu are complex conjugates of each other. That symmetry is no accident. This cyclic structure is the entire proof hiding in plain sight. Now the decisive question. If each side of the center triangle is just a rotation of the previous side, same length, just turned, then the triangle must be equilateral. That's literally the definition. Your first instinct might be to compute all three side lengths separately, but there's a much more elegant approach. Check if one side vector is a fixed rotation of the next. We want some rotation factor omega such that the next side equals omega times the previous side. Working through it, omega must equal negative mu over lambda. And for omega to be a pure rotation, same length, no stretching, we need the magnitudes to match. That boils down to one clean identity that lambda and mu must satisfy. Let's verify that identity. We need to compute three terms and check they cancel to 0. Watch each computation on screen. The key insight, lambda times mu simplifies to exactly 1/3. This makes sense because lambda and mu are conjugates, so their product is just the squared magnitude, a real number. Now add the squares and subtract the product. The imaginary parts cancel. They always do for conjugate pairs. And we're left with 1/3 minus 1/3. 0. The identity holds. So omega is a rotation by exactly 120 degrees. And this makes sense. 120 degrees is 1/3 of a full turn, which is the defining symmetry of an equilateral triangle. And there it is. Each side of the Napoleon triangle is the previous side, rotated by exactly 120 degrees, same length, perfect threefold symmetry. No matter what triangle you start with, tall, flat, obtuse, or nearly degenerate, those three equilateral triangle centers always form a perfect equilateral triangle. That's Napoleon's theorem proved. The key insight was that cyclic structure, the same two weights rotating through the vertices, force a 120-degree symmetry between consecutive sides. This idea of building new shapes on old ones and finding hidden symmetry is exactly how crystallographers design lattice structures, and how architects create tessellating floor patterns. Next time you see any triangle, imagine those equilateral triangles blooming outward. Hidden inside is always a perfect equilateral triangle. If you enjoyed this, like and subscribe for more.